Okay, so we're building off of what we did yesterday. The problems will look a little different, but we'll go over what's different about these. But I do want to point out something from yesterday. I didn't quite go over number 5, but on page 24. But I put the key up. I just want to point out a few things here. It's straightforward in the sense that we're just adding the 2 vectors to create our resultant vector. And from there, you're just getting to your direction and your magnitude. But here, notice that part B, it says find the direction in terms of bearing. So what I did was I found it in terms of the standard position. So I knew that my let's see, for part. Oh, yeah. For part B, I knew that I was pointing in the first quadrant. Because of that, both my horizontal and vertical components are positive, and I got 25.627 degrees. But it's asking for bearing. So bearing is in terms of, it's basically measured from 90 degrees. So you can either do 90 minus that degree measure, or you could do this. You can also play with 450, and that's the same process. So to get from bearing to position, standard position, or from standard position to bearing, you can just involve 450. Now, it may seem a little bit off when you try to do it, because you do 450 minus your standard position. I try to do that, right? 450 minus 25.627. Notice that I get 424, which doesn't seem like a bearing that I want to use, because I should be between 0 and 360. So if it doesn't fall in that 0 to 360 range, you can just keep subtracting 360 until you get to the bearing that they're looking for. Does that make sense? So we know how to get from bearing to standard position, but if at the very end they say, hey, give the direction in terms of bearing, I would get to the standard position and then subtract from 450. And if it doesn't quite fall in that interval, subtract another 360 to get into that degree measure for bearing. So that's why for part B, the answer is not 25 degrees, because it's asking for bearing. Okay, so let's go over example 1 on page 25. So it says, to reach a destination, a pilot is plotting a course that will result in a velocity of 450 miles per hour at an angle of north 60 degree west. So this is what's different here. The difference is that it's not asking, the pilot is not focused on where the plane is pointed. It's focused on the resulting vector. So what's given to you is the resulting vector. Okay. The wind is blowing at 50 miles per hour to the north. Find the direction and speed that the pilot should set to achieve the desired resultant. So this pilot is almost going to have to point the plane in a different direction than where he's headed, because he's adjusting for the fact that the wind is going to be blowing. So he's almost has to counteract against the wind to eventually reach this goal, right? So his goal is to eventually have the plane pointing in this direction after the wind is blowing, but you got to point in a different direction to get that result. But we can set up using the same formula, right? We know that the vector for the plane plus the vector of the wind is going to give us the resulting vector. Okay, so we have information about the resulting vector. We have information about the wind vector. We just have to work backwards to figure out what is the vector for the plane. So if I want to solve for vector P, that's equal to what? Yeah, it's going to be my resulting vector minus the wind vector. Okay. Does that make sense? So let's go ahead and find those two information, right? Let's find the resulting vector. 450 miles per hour at an angle of north 60° west. So north 60° west, let's go ahead and draw that out. That means I'm starting at 90 degrees and I'm moving 60 degrees to the west. So what is the standard position of north 60° west? 150, right? Because I'm starting 90 and I'm going into the second quadrant, so I got to add 60. Okay. So my theta is 150. Okay. So I have my magnitude, I have my direction, so I can use sine and cosine to get it into component form. Okay, my wind vector blowing 50 miles per hour to the north. So what's my wind vector? 0, 50, right? But I'm going to have to subtract it, right? I'm not going to be adding the two vectors because I'm doing resulting vector minus wind vector to get to my plane vector. So I'm going to just subtract the vectors or subtract the wind vector. And that will get me to my plane vector. So we can use our calculator, 450 cosine 150 minus 0, and then 450 sine 150 minus 50. So now that we have our plane vector, we can find the direction and the speed that the pilot should set to achieve the desired resultant. Okay, so Pythagorean theorem will get us to our magnitude. And then which quadrant should he point his plane? Second quadrant. So whatever we get from inverse tangent, we gotta involve 180, right? Okay, example 2, we haven't seen problems like this, but I'll walk through it step by step. a traffic light at an intersection is hanging from two wires of equal length, 15 degrees below the horizontal as shown. If the traffic light weighs 560 pounds, what is the tension in each wire keeping the light at equilibrium? So let me kind of show you how we're going to start this. We know that the weight of this traffic light is pointing downward, so that's 560 pounds. Okay. Now these are the wires are, think of this as the hypotenuse of these vectors. Okay, so if we can just imagine a triangle here.
Okay, I think I also will check this one. Should I just, we already heard it. I just want this one.
So what we want to understand is that this 560 pounds is going to be, has to be balanced with the vertical component of the two wires that are maintaining it at equilibrium. So that 560 pounds is going to be split between these two vertical components, pointing in the other direction, right? That's the only way that this traffic light is going to stay stable and not move. So what's 560 divided by 2? 280. So we have these two wires that both have a force of 280 pounds pointing the other direction to maintain that downward force from that traffic light. Okay. Now something else here is that theta. Okay, that theta is from that 15 degrees here at this upper corner. But we really want to be working with this triangle that we have below here. So I'm going to transfer that 15 degrees over to here. And the reason why we can do that is because these are alternating angles from this transverse, right? So because we have parallel lines with the transversal going through, we know that alternating angles are congruent. So that's why that 15 can be transferred from one space to the other. So now it's asking, what is the tension in each wire keeping the light at an equilibrium? All right. So what we can do, we can just try to find that. Let me draw this out again. We're just going to find the hypotenuse. Right, I got my 15 degrees. I got the 280, and I'm just looking for the magnitude. So I can use trig, right? What trig function can I use to help get to the hypotenuse? That sign. And it's only asking for attention in each wire, so I just focus on one triangle, and that's all I need. So sine of theta, which is 15 degrees, equals opposite over hypotenuse. Cross multiply, solve for my magnitude. Now, in this case, everything is in terms of pounds. Our magnitude is also in terms of pounds. Thank you. Oh, okay, hold on, I copied it wrong. Sorry, you're right, 1081.837, I copied it wrong. Okay, we'll see another problem like this on the back page, but wanted to go over first one with you. Okay, any questions with one or two at the top? Okay, so let's look at number one, halfway down. This should be more straightforward. We're just gonna be adding the result of those two vectors. This is, one of the names is wrong. So I'm gonna read this here. Ann and Mike are lifting a stone statue and moving it to a new location. Ann is pushing the statue with a force of 120 newtons at a 60-degree angle. Well, this is meant to be Mike here. Well, Mike is holding the statue with a force of 180 newtons at 40-degree angle. What is the magnitude of the combined force that they exert on the statue? Okay, so basically we can just find vector for Ann in component form, find the vector for Mike in component form, and that'll get us to our resultant vector. And once you have your resultant vector, then you can get your magnitude using Pythagorean theorem. All right, try that. Pretty straightforward, should be similar to the process that you went through yesterday with those four problems that we worked on. Thank you. Sure. All right, let's check our answer for one. Resultant vector will just be adding the horizontal vertical components, and then it's just only asking for magnitude, so Pythagorean theorem, square roots. All right, try number 2 on the next page. Very similar to the setup that you did for the traffic light. Very similar. So let's see if you can look at the traffic light problem. I'll put the traffic light problem up on the board so you can see it and kind of follow the steps similar to the one that we just did. The same idea, you have to balance out whatever is the weights with the vertical components going the other direction. And then again, you'll use sine to solve for your hypotenuse. Number 2. Any questions for 2? Okay, so number 3. 3 is the setup is a little bit different here. This is the person in the canoe wants to cross a 65-foot wide river. And that 65 is really not going to play a role in this problem because everything's in terms of velocity here. So let's say we have a river here. He begins to paddle straight across the river at 1.2 meters per second, while a current is flowing perpendicular to the canoe. If the resulting velocity of the canoe is 3.2 meters per second, what is the speed of the current to the nearest tenth? So we can label everything here, right? Here I have the magnitude for my canoe. Here, I'll just do P for the person here. The current is perpendicular, and then the resulting vector is here. So we know that vector P, C, and R, they're forming a right triangle. So I can, if I know the magnitudes of two of them, I can just use Pythagorean theorem to find the magnitude of the third one. Right? This is only asking for the magnitude, and we can just completely ignore the direction is already taken care of, and it's a right triangle. So we know that P squared plus C squared equals R squared, right? We have that relationship because it's a right triangle. Okay, so we know vector P is 1.2, so I can say 1.2 squared plus the current squared is equal to the resulting vector squared. Now I just have to solve for C, and that's it. Okay, two more. Number 4 should be straightforward as well. See if you can work through that. We have vector 1, vector 2, add those together, add those two component forms, and you get your resulting vector. The only thing is at the end, when you solve for theta, you just have to convert it back to bearing. So whatever theta you get, just subtract from 450. So solve it the same way that you would any other problem, just at the very end, you have to make an adjustment. All right, so try 4. All right, so Kristen walks north 70° west, so that means she's starting at 90 degrees and she's moving to the second quadrant, so 90 plus 70 is 160. So that's, the first sentence will give you your information to create your first vector in component form. And then the second leg of her trip, she walks due east for 90 meters, so she's going to the right. So that's just 90 comma 0. How far and what and at what bearing is Kristen from her starting point? So I'm just going to add the two vectors together. Get the magnitude, and that will get us the distance. And then inverse tangent will get me to my reference angle. I know that my resulting vector is 20 in the second quadrant, so I just have to subtract from 180. So I get 180 minus 34 degrees, which is 145 degrees. That's standard position, but it's asking for bearing. So I just subtracted my theta from 450, and that gets me to my bearing measure. 450 minus 145 is 304.
There's a meter, is that the magnitude?
That's the magnitude. Yeah. So sometimes the magnitude is in terms of velocity, sometimes it's in terms of meters. It just depends on the context of the problem.
Okay.
Yeah. Mhm.
So use the magnitude formula here to solve the distance instead of the distance formula.
Well, we've always used Pythagorean theorem,
Yeah.
right? So it's the same process, right? Same process. I think they. Okay, questions for? It's just that the only thing that's different here is having to make that adjustment to get from your standing position to bearing. So that's the only thing that may feel a little different because we haven't had to do that yesterday. Okay, any other questions here? Now, there's something a little weird about number 5. Let me talk about that issue first before you guys try it. So there's a distinction between wind blowing towards 192 degrees versus wind blowing from 192 degrees. So if I'm blowing towards 192, that's straightforward, right? I'm just going directly into that third quadrant, and that wind is blowing in this direction. So that's my wind vector in the third quadrant. But if the wind is blowing from 192 degrees, then it's coming towards, not away, but towards. So that's going to end up in which quadrant? The first. So basically, I'm going to just follow that line and go the other direction into the opposing quadrant. So what is that going to look like? Well, 192, the reference angle is really helpful here because we know that 192 is really 12 degrees from the horizontal. So that means if it's blowing in the 180 degrees away, it'll be 12 degrees, right? I can also subtract 180 from 192, and that will give me the same thing. So basically, I'm just having to adjust it to go the completely opposite direction. So that's what's different here. So the wind blowing from 192 is really telling you that you want to use theta equals 12 degrees. Okay, so try that. See if you can use that to help you set up number 5. But number 5 is also one of those problems that you got to do some subtraction, right? Because we don't know where the plane is pointing at. We do know the wind, and we do know the resulting vector. So again, similar to the previous page, our vector P plane is going to be the resultant minus the wind. Make sure that we're subtracting the wind vector. So negative 500 minus 100 cosine 12, 0 minus 100 sine 12. And once you get to the plane vector, then everything should be straightforward. Pythagorean theorem gets you to your velocity, magnitude, and then inverse tangent will get you to your reference angle and the which quadrant is this pointing in. And the resulting vector is in the third quadrant, so we got to add 180.
Can you explain again, like the wind blowing from when I was doing it?
Yeah, so if the wind is blowing towards 192, then you know it's in the third quadrant. But if it's blowing from 192, that means it's not going away, it's going in this direction. So that means it's going in the opposite direction of 192. So if I know that opposite is just 180 degrees away, I can do 190 minus 180, and that will point me in the other direction. Yeah.
How come 20.7 and one is negative?
Because our formula says the resulting vector minus the wind gets to our p, so I have to subtract. Yeah, normally we're used to vector p plus vector wind and getting to the resultant, but here they give us the resultant and wind, they don't give us the initial plane, so we gotta subtract. Questions? Okay, so we've covered all the new material. Monday and Tuesday will be test review. Wednesday will be our test. I hope to get back your quizzes on Monday. I'm gonna try to shoot to get back your quiz by Monday. Yeah. All right, don't get your phone. So there's line that everything's on.
Oh, that's probably fun.